Hello everyone, hope you are doing very well and enjoyed previous lecture. In this lecture, we're going to be discussing about Kruskal's algorithm for finding minimum spanning tree. In the previous lecture, we discussed a generic algorithm for finding minimum spanning tree of a graph, what are spanning trees, and an example of a hypothetical digital circuit. We converted that digital circuit in a graph form, and then we found a minimum spanning tree of that graph. We're going to be using the same graph algorithm for this algorithm as well. The key idea behind Kruskal's algorithm is that let's sort all the edges by their weight, and once we have sorting of the edges, then we determine the safe edge. Okay, so we first pick up the minimum weight edge and see whether both ends of the minimum weight edge they belong to same tree or not. If they belong to same tree, it means they might form a cycle and that edge is not safe to add. However, if they do not belong to the same tree, it means we can safely add that edge in our set of edges for spanning tree, minimum spanning tree. Okay. So initially we have a forest, uh, and this algorithm uh, assumes that in the very beginning each vertex is represented by a independent tree. Okay, so initially as many vertices you have in the graph, as many trees you will have, and then slowly those trees will be joined together as we keep on finding the next minimum weight edge. Okay, so let's see how the algorithm is. So initially we have no edge, or we initialize basically our spanning tree. Okay, T is nothing but the set of edges which will represent our minimum spanning tree. Okay, for each vertex in our original graph, we execute a operation make set. Make set is nothing but it is basically creating a forest of trees, and each tree will have only one node. Okay, that is the each vertex of the graph. At line number 4, we are sorting the edges of this graph in a non-decreasing order by weight. And at line number 5, for loop, for each edge, okay, we determine whether that edge will be safely added to T or not. Okay, so what it means that we execute line number 6 means find set U is not equal to find set V. So we take a decision for both the ends of this edge. Let's say we say the edge AD. So if A, okay, if some set or some tree has A, that should not have D in order for that edge AD to be added to T. Okay, so if this does not equal to, say, find set A is not equal to, so if find set A is not equal to find set D, it means that you can safely add that and make a union of these two sets or these two trees A and D. Okay, so let's see how this algorithm proceeds further. Initially we have no element in our set T, and we have forest, okay, or we have these vertices as independent trees, okay. Now after sorting the edges, we find edge A and D and edge C and G. Two edges have the lowest weight, okay. So let's pick A and D first. So we pick up A and D, and now we determine, we are at line number 6, we determine whether A and D, they belong to the same set or not, or they belong to the same tree or not, and they do not belong to. A is independent and D is independent. They are independent, and we can safely now add edge A and edge between A and D to T, right? And the tree would look like A and then T. A is connected to D, okay? That our minimum spanning tree would look like that at this stage. Now algorithm proceeds forward, and we find that, okay, C and G, edge between C and G, and we execute line number 6. We find that, okay, C and G, they do not belong to the same set, so we can safely add edge C and G to T, and our resultant graph or minimum spanning tree would look like something like that. Okay. Then next stage, we found the edge between A and E has next minimum weight, that is 3, and we execute line number 6. Find set U means find set A is not equal to find set E. Okay. So in this tree we have A and D. Okay. So we found, okay, we found the A is existing in our tree, but E is not there. So we safely add this edge between A and E, and our tree would look like this. Next, we found the edge between B and F. B and F, they are not together, and we can safely add that edge as well, and our forest would look like B is connected with F. Okay. Next is B and G. Okay. So same thing, the edge between B and G, and let's say B belongs to some tree and G belongs to a different tree. Okay. So G is with the C, B is with the F, two different trees. Okay. We can safely add that edge in our spanning tree edges. B and G we have added, and our tree will, after merging the B and G, that's how our forest would look like. Okay. So as you can see here, we have merged G and C tree with the tree B and F. All right. Next, we found that, okay, the edge between A and B, it has the next lowest weight is 4, and we take the same decision whether A and B belongs to the same group or not. They do not belong. We can add safely A and B to our minimum spanning tree, and our resultant tree after the union would look like that. Now here, see, we have still 5 8, 8, 3 more edges left. Now let's look at the edge with weight 5 between D and E. Okay, so if we take D and E, is it a safe edge or not? So if we execute this operation at line number 6, find set U means find set D, find set D, and then find set E, and that will be equal to actually, okay, because these belong to the same tree now. So we do not execute line number 7 and 8, otherwise it will form a cycle. So see how line number 6 is making sure that we will not form any cycle, and we would end up getting a minimum spanning tree. The same way we can think about the edge between B and E and the edge between E and F. Okay, these two also will form cycle, so these will be eliminated or discarded by the condition at line number 6. Good, very simple algorithm, very straightforward. Pick the minimum weight edge after sorting all the edges. That's the simple keyword here for Kruskal's algorithm. Now let's look at the complexity of this algorithm. Okay, so initialization step can be done in O1 time, and then make set V line number 2 to 3. These will take in the order of V, as many vertices we have. Okay, and sorting operation will take E log E. So as you can see here that mainly, okay, our algorithm would take, say, V plus E log E time. Okay, now let's observe a fact that E is less than V square. Okay, here is number of edges, V is number of vertices in our graph, and we can also say that log E would be in the order of log V. Log of E would be in the order of or equal to order of log of V, or in other words we can say that the overall complexity of this algorithm would be in the order of E times log V. Great. So thank you guys for liking and subscribing with Lee Professor channel at YouTube. Thank you very much. Hope you have enjoyed this lecture. Thank you very much for your comments, suggestions, feedback, and have a wonderful day.